Good day, one and all. We are welcome to the HESA e-library, also known as the HESA video bank. Today we are discussing hydroxy acids and the organic chemistry too, right? So without much ado, let's just dive into it. Now, under hydroxy acids, we'll talk about Reformatsky reaction. We'll talk about lactides and lactones, right? All right. Now, this particular piece has pictures. Pictures of significance. We are looking at either artificial or man-made products which contain hydroxy acids like skincare products. And then we also have natural products like the vegetables and the milk on our screen, which also contain hydroxy acids, right? So these show us the practicality of the topic that we are about to read. Now, introduction. The first statement is defining what we mean by hydroxy acid. Now, we are saying in simple terms that it's a single organic compound that contains both a hydroxyl group and a carboxylic acid functional group. Now, that should make sense because the compound is called hydroxy acid. Hydroxy because it contains a hydroxyl group, and an acid because, of course, it contains the the carboxylic acid functional group. A typical example is what has been drawn here, lactic acid has been drawn here for us. That's a very typical example. So we can see the hydroxyl group here, and then the carboxyl group or the carboxylic acid functional group there. Now, the second statement is saying hydroxy acids are important organic acids. They occur naturally as well as synthesized by different chemical and enzymatic reactions. They are used as cosmetics, drugs, or drug precursors, right? This would also be important to the pharmacist. Now, we have been given examples of hydroxy acids. The first in no particular order is glycolic acid. Now, arguably, glycolic acid is the most basic hydroxy acid that you can find. Now, you will find it in sugarcane. Right, so this is the structure of glycolic acid. So it's like ethanoic acid with an OH substituted for H, right? So the hydroxy acid, and this is the simplest that you can find. Now, glycolic acid is used as a flavoring agent and preservative and can also be used in some skincare products. The next one here is lactic acid. We have already come across lactic acid now. It's in sour milk, right? And then it can also be produced in the muscle upon prolonged exercise. Now, the next one we have here is tartaric acid, which is one like the first two, a dicarboxylic acid, right? And then it has two hydroxyl groups too, right? Now, tartaric acid can be used in some medicinal preparation. The next one is malic acid, which is found in grapes and apple, right? Now, malic acid is like tartaric acid without one of the OHs, right? That one of the OHs, so that is what we can see here. So the only difference between tartaric acid and then malic acid is the loss of the OH group on this carbon, right? Now, citric acid, on the other hand, is quite different. It's a tricarboxylic acid. A tricarboxylic acid, of course, it is found in citrus fruits, citric acid, right? It's found in citrus fruits. Very simple. Now we have to know the structures or be able to identify the structures of these compounds upon seeing them, right? They will come up a lot, and once we see them, we have to be able to identify the compounds. Now, classification, we have three different ways of classifying hydroxy acids, but in this particular discussion, the last one will be what will be of importance to us. So we'll talk about the first two, but we'll stress on the last one. Now, the first one is based on the number of hydroxyl groups. So if you are grouping the hydroxy acid based on the number of the hydroxyl group, we would have mono or poly, right? Mono or poly. Some people bring di. So mono, poly, tri, it goes like that. Now, there's an example of mono. Mono because this is the carboxyl group. It has only one hydroxy group, or the hydroxyl group is just one. Now, if you look at the poly, this is the carboxylic acid group. That's not what we are looking at. The hydroxyl groups are a lot. They are more than one, right? So that gives you the poly. Very simple classification. Next one is the nature of the carbon skeleton. That is either whether it is aliphatic or aromatic, right? So the examples have been given. This is aliphatic, and then these two are aromatic, of course. This one is directly aromatic because the groups of important are directly substituted on the aromatic ring. But then if you look at this one, there's an aromatic ring, of course, but then this side is aliphatic chain. This side is an aliphatic chain. So it gives rise to another one, which is a hybrid. We call it the aryl aliphatic hydroxy acid. It means it's an aryl group, right? That's aromatic. And then there's also an aliphatic group. That is the straight chain that we have here, right? Now, position of the hydroxyl group on the carbon. And this is the most important classification. In that, we would have alpha, beta, gamma, delta. Then we go on like that. Now, they have given us example. Let me explain how we classify this. And so if we have, let's say, carbon, COOH, this is the carboxyl group, right? The carboxylic acid functional group. Now, the next carbon here is the alpha carbon. So if the OH happens to be on the next one, so this is carbon 1, the carbon 2 is the alpha carbon. If we have the OH substituted here, then we have an alpha hydroxy acid. Now, if the OH is not here, right? If the OH is not here, but on the next one, so number 3. Now, if this is alpha, this is beta. The next one is gamma. The next one is delta, right? And so depending on where the OH is substituted, we will have an alpha hydroxy acid. When it's substituted on carbon 2, we can have a beta hydroxy acid, we can have a gamma hydroxy acid, and we can have what? A delta hydroxy acid. Now, all these hydroxy acids will behave differently. And this is a particular classification which is of importance when we are looking at this particular topic, right? Now, so we have been given examples. Now, this is COOH, right? And this is alpha. So this is the alpha carbon. We have alpha hydroxy acid. This is COOH. This is alpha. This is beta, right? So it's on the beta that we have the OH group, beta hydroxy acid. Now, this is COOH functional group. This one is alpha, beta, gamma, right? So on the gamma, we have the OH directly bonded, and so that's a gamma hydroxy acid nomenclature. Now, there are two different ways of naming. First of all, is the common name. I mean, we can look at the common name. The common names can be the general names that we have, but we can still have common names, which are done by using the Greek letter, that is either alpha, beta, or gamma, as a for the hydroxy acid as a derivative of their parent name of the parent acid. So if you are looking at the examples, I mean, most of the examples have been named already, right? But let's look at how we arrive at that. Now, this would always be carbon 1. The next one here will be the alpha carbon. Next one will be the beta carbon, right? I always name from the parent chain. So carbon 1, 2, 3. Now, the longest chain is 3 carbons. It's an acid, so it's propanoic acid, right? Now, we have the OH group on the alpha carbon, so that becomes alpha hydroxy propanoic acid, of course, known as lactic acid. And if you look at this one, we have 1, 2. 2 carbons is ethanoic acid or acetic acid, right? Now, the OH is on the alpha carbon. The alpha carbon is the carbon next to the most important carbon, the carbon next to the carboxyl group, the carbon next to the carboxyl carbon, right? This is the carboxyl carbon, so that's what I'm talking about, right? To alpha hydroxy acetic acid, alpha hydroxy ethanoic acid, yeah, so that's it. That is glycolic acid, for us. Now, the next one we have succinic acid. So 1, 2, 3, 4. So a dicarboxylic acid, 4 carbons, that's succinic acid. Now on carbon 2 and carbon 3, we have OH groups, but then we don't name, when in terms of common names, we don't do that. So this is an alpha carbon when you are looking at this. This is also an alpha carbon when you are looking at this carboxyl group. So we just bring prime to separate them, right? And so we'll have alpha prime dihydroxy succinic acid, right? Yes, because both of the carbons, they are essentially alpha carbons. Now, the last one here, the same thing, we would have 1, 2, 3, 4. Now, there's only one alpha carbon here. So this one, right? There's only one alpha carbon here, this one. So that gives us alpha hydroxysuccinic acid. That can be difficult, can it? Now, when we are done with this, we have to also learn how to give the IUPAC name, right? Now, the IUPAC name, we use numbers. We don't use alpha, beta, and gamma. We use numbers to name the substituents or the hydroxyl group. So the first one here. Now, instead of making it alpha hydroxypropanoic acid, I'll make it 2-hydroxypropanoic acid, and I'll get the IUPAC name. Now, this particular one, instead of making alpha hydroxyacetic acid, I'll make it 2-hydroxyethanoic acid, and I'll get the IUPAC name. Now, this is succinic acid, but the actual name, if you are looking at IUPAC, is butane dioic acid. Butane dioic acid. And so what we have here, if you are looking at it in essence, we would have, instead of the alpha, we'll have 2,3-dihydroxy, 2,3-dihydroxy butane dioic acid, right? So that's what we have here. Now, this particular one is still butane dioic acid, and we'll have just 2, so 2-hydroxy butane dioic acid. That can be difficult. Now, the last one we have not touched is this one, the tartaric acid, sorry, the citric acid here, the citric acid here. So let's look at how we can name that citric acid. Now, this is a tricarboxylic acid. Tricarboxylic, this is how I will number it. I will not number the carboxyl groups. I will start numbering like this: 1, 2, 3. I can number from this end: 2, 1, 2, 3. But then both of them will be the same thing. Now, the 1, 2, 3 will give me the parent name of propane. Now, this is how I bring the 3. So propane tricarboxylic acid will be my parent name. I have to show where the 3 carboxyl groups happen. So I will say the parent name will be 1, 2, 3 propane tricarboxylic acid. Propane tricarboxylic acid. That will be the parent name. 1, 2, 3 propane tricarboxylic acid. Now the substituent will be hydroxyl group on position 2. And so I'll have 2-hydroxy propane, sorry, 2-hydroxy 1, 2, 3 propane tricarboxylic acid, right? And that is what we have here. Right now, if you look at these examples, you can try more, but then it will help you generally to predict the names or determine the names of all the other hydroxy acids that you come across. Now, physical properties of hydroxy acids. The first one we are seeing is hydroxy acids are colorless liquids or crystalline substances. In terms of solubility, we are seeing hydroxy acids are very soluble in water because both functional groups, OH and the COH, do form hydrogen bonds with water, right? And then that makes sense. So this group is highly polar. It has 2 different functional groups, and both of them can form hydrogen bonds. So it's very soluble in water. Now, we are seeing the melting and boiling point of hydroxy acids are higher than that of the unsubstituted corresponding acids due to hydrogen bond formation. So once again, we would have a higher intermolecular interaction, right, between the molecules of hydroxy acids. That will afford them a higher boiling and melting point, right? A higher boiling and melting point. Good. Now, the last property we are looking at here is the acidic property. Now, let me draw something small here quickly for us to look at. Now, this is C double bond O. OH. This is the niche. This is the carboxyl functional group. Now, if I'm talking about an alpha hydroxy acid, the OH should be here, right? Now, this is a hydroxy acid. Hydroxy acid. What we are saying here is that the region or which part of the compound that will be responsible for the acidity of the compound will be this OH group, the OH group on the carboxyl group, right? Now, what happens is that this OH group here, the hydroxyl group here, can pull electrons. Now, the electron pulling here is essentially through inductive effects, negative inductive effect, right? So you pull electrons through the sigma bonds, pull electrons, pull electrons, pull electrons, and the electrons are also pulled here, such that this OH bond here becomes highly polar. Now, when the OH here bond is highly polar, this bond is very weak, right? Very weak, and so it can easily lose the hydrogen, right? And so the carboxyl group here, the acidity of the carboxyl group is enhanced due to the electron withdrawing effect of the OH group here, and that is the English that has been written here, that hydroxy acids are more acidic than corresponding acid because of the electron withdrawing effect of the OH. I have explained this. Synthesis. Now, for the synthesis, the way or the method for synthesizing alpha hydroxy acid is different from beta in a significant way and different from gamma and delta. So we'll take each of them one after the other and talk about it. The first one would be how to synthesize alpha hydroxy acid. Now, if you want to synthesize alpha hydroxy acid, the first way is from a halogenated acid. Now, using this particular way, you have to get an acid that has already been halogenated at the alpha position. If you look at this example, the chlorine is on the alpha position. This is the most important carbon. This is alpha carbon, right? Now, what we'll do is that we'll add the base 2 moles of sodium hydroxide. And then, first of all, we'll have an acid-base reaction. So you see a salt form at this end, and the chlorine will be replaced with an OH. Later, then we have to acidify. We have to acidify to get back our acid and then remove the salt. Reverse the salt and get back our acid. And this is the acid that we have produced. This is one of the ways of synthesizing an alpha hydroxy acid. Now, the next one from amino acids. So if you want to use this method, you have to find an amino group, right? The amino group should be already attached to the alpha carbon. That's what we have here. So we have this alpha amino group, right? And then we add nitrous acid. We add nitrous acid, and then we'll come and get our lactic acid here. Very simple. Now the last method is oxidation of diol and hydroxy aldehydes. Now, the two things are the same one, depends on where you are starting from. So this particular pathway shows us when we are starting from a diol. So you take it from a diol to a hydroxyaldehyde, and then you take it finally to your hydroxy acid. Now, the oxidation that's happening here, we are doing oxidation, right? We are doing mild oxidation, not drastic or strong oxidation, mild oxidation. And so if you have your diol, you can oxidize this mildly to aldehyde, right? So the terminal OH here can be oxidized to an aldehyde, and then the aldehyde functional group can also be oxidized to a carboxyl group, and then that will give us our hydroxy acid. Now, this particular schematic pathway should be mild because if it is a strong oxidizing process, it can affect this OH. This OH will be affected to convert, we'll get something like a keto acid, right? And so in order for us to get our hydroxy acid at the end, we have to take it slowly. We have to do mild oxidation first step and mild oxidation the second step. Very important. Now, the last way through which we can synthesize hydroxy acids, alpha hydroxy acid, is the hydrolysis of hydroxy nitrile or cyanohydrin. Now, the schematic pathway doesn't show us from that end. It shows us from before how we can get our cyanohydrin. So the paragraph here reads, hydrogen cyanide adds to carbonyl groups of aldehydes and most ketones to form compounds called cyanohydrin. So what we have here, usually we have a ketone and an aldehyde, and then we add hydrogen cyanide. Now, when we add, this is what will happen. The double bond here will break. The double bond here will break, one of the double bonds. So the pi bond essentially will break. This carbon will form a new bond with a CN, and then an H will be attached here. Right, so that is what we have at the side. And then in the next step, now when we form this is what we call the cyanohydrin or the hydroxynitrose. So this particular process starts from here. It starts from here. Right, it starts from here. That's if you are looking at the name. The hydrolysis is actually this step, just the step, the final step. But this schematic pathway, or almost always when you have a question, you would have to take it from the aldehyde or the ketone form to your cyanohydrin before finally you can convert from your cyanohydrin to your alpha hydroxy acid. Now, you can finally hydrolyze this nitrile group. So we can hydrolyze, we can do hydrolysis of this nitrile group, right? Or the cyanide group to carboxylic acid. So finally, this one breaks to COOH. That is what we have here. Now, the good thing about this particular, the different thing about this particular schematic pathway is that at the end of the day, it will add one extra carbon to what we have initially, to what we had initially. So if you look at this, let's say this was one carbon, this was another carbon. At the end of the synthesis, you realize that we have 1, 2, 3, right? And so if a question comes and you are supposed to use this, typically you realize that between the reactant and the product, the number of carbons has increased by 1. Number of carbon have increased by 1. That's what would give it away that you are supposed to use this method. Now, another example has been given to us up here with the skeletal structure. That shouldn't be too difficult, right? So we have the ketone, and then we add the cyanide to get our cyanohydrin. Then we hydrolyze finally to get our hydroxy acid. Now, an example for us to try. Definitely, this is directly under the cyanohydrin hydrolysis, and so we know we'll have to use the method up here. But then even without that, look at something. We have 1 carbon, 2 carbons, right? So now here we have 1, 2, 3 carbons. This one typically suggests that we have to use this particular method. So what would we do? Now we'll add this to CN. When you add CN, what will happen is I would have one of the double bonds breaking. Then this C will form an extra bond here, the CN, right? And then an H will be here. Now in the next step, that will be the first step when I add HCN, right? The next step when I'm hydrolyzing with an acid as has been shown here, I will have this N being moved away. So the N being moved away, right? And then the N will change to COOH, right? And so that is what I'll have. Very simple. And that should be exactly like this one, the product that we have here. Now, the chemistry is always a science, but it is also an art. So sometimes when I'm showing you how compounds will just turn from reactants to products without explaining the mechanism, it means at that point I am focusing on chemistry as an art. The responsibility is to understand the art. Synthesis of beta hydroxy acids. So we are saying we can synthesize beta hydroxy acid by hydration of alpha beta unsaturated carboxylic acid. This is a very simple synthetic pathway, but this is not the major pathway for synthesizing beta hydroxy acid. The major way to synthesize beta hydroxy acid is through the Reformatsky reaction, right? Now, this is a minor way, and I'll explain why it is minor. So all we have here is a simple addition reaction, right? We have an unsaturation. This is the functional group we are interested in. So we have a simple unsaturation, and then we are adding water. Now the water will add as OH to one carbon and then H to another carbon, right? Yes. Now this addition will normally follow Markovnikov. Now, if you are following Markovnikov addition, what we have to do is that we have to add the hydrogen to the one that already has more hydrogen, right? Now, if I am supposed to do that, now what this is what will happen. I'll break one pi bond. Now, when I break one pi bond, this one has an opportunity to form an extra bond. This one can form an extra bond. If I'm following Markovnikov, I'll put H here because this one has two H's and this one has one. Now I'll put the OH here. Now this one still gives me an alpha hydroxy acid. And I will only get a beta hydroxy acid if I'm supposed to add it in the anti-Markovnikov way, which will give me the minor product, not the major product, the minor product. So if I'm supposed to do it as we have here, I have to put the OH on this one and then the H on this one to get a beta hydroxy acid. And that is a minor product. So this is not the major way, but this is one of the ways for getting a beta hydroxy acid. That's hydration of alpha beta unsaturated carboxylic acid. One of the ways. But the major way I have said is using the Reformaski method. Now, the next thing that we can synthesize, we can also synthesize gamma and delta hydroxy acids. Now, what we have to do is that we have to get a chlorinated acid, right? So now the chlorine or the halogenated acid, the halogen should be exactly where we want the OH to be. So if we want to synthesize, let's say gamma, right? The chlorine should be on the gamma position. So that is what we have here. Now, this is gamma, right? This is the gamma carbon. This is alpha, beta. Sorry, my gamma this is gamma. So we first of all add the 2 moles of any OH. It would react to get us a salt, and then an OH will be here. The OH will be here. And then finally, we acidify to get back our acid here, and that will give us this gamma hydroxy acid. Very simple. Now, Reformaski reaction. We are saying Reformaski reaction is the most important method for preparing beta hydroxy acid and their derivatives. Now, the Reformaski reaction is an organic reaction which condenses. Now, these are the materials we need. We need either an aldehyde or a ketone. Then we need an alpha haloester. And then we need zinc metal. Now, what we form out of Reformaski directly is not a beta hydroxy acid, no. But what we form directly is a beta hydroxy ester. Just after getting our ester, we can hydrolyze the ester to form an acid. Good. So now the next statement says the ketone and the aldehyde, or the aldehyde and the alpha hydroxy ester can be reacted to form beta hydroxy ester. The beta hydroxy ester is easily dehydrated to an alpha beta unsaturated ester. So let's look at the reaction pathway. Now we have the carbonyl here, an aldehyde or the ketone, plus zinc, plus the alpha halo ester, and that will give us a beta hydroxy ester. At this point, I just want us to know how to convert the reactant to the product. And so what will happen here in essence, now this is the ester. The most important carbon is this one. This is the alpha carbon. We have bromine there. Now the reaction will occur at this point where we have the alpha carbon. The rest of the compound will remain the same. Now, and then this carbonyl. So it will occur between this carbon and this carbonyl. So what we do, in order to write your product, what we will do is that we will remove the bromine. So we'll take the bromine off. Now we'll connect this carbon directly to this carbon, the carbonyl carbon. Reduce this double bond. So remove this double bond and then add H. Remove this double bond and add H to the oxygen here. Right, so bring the pi bond and add H, and that will essentially be my product. So that is the product that we have here. That's this product. This carbon is the one that had the Br. We have removed the Br. This is the carbon that was the double bond O. Now it has the OH, right? Good. Now, in the same way, we have to be able to also predict the reactant from the product. So if we are predicting the reactant, what we do is that we stand here. Now, this is the carbon. that has the O. This is the carbon, the alpha carbon. We divide between the alpha carbon and the carbonyl carbon. Now 2, the carbonyl carbon, we remove this hydrogen here and then bring a double bond, right, to restore this. Now 2, the ester part, when we cleave this, we just put a Br here. Now it's just a reverse of what we did because we removed the Br in the other sense. So now we'll have our Br and then we'll still get our alpha halo ester, and all we have to do is to add zinc. Now this is the intermediate form, and I'll explain the intermediate in the next slide, right? Now this is a schematic representation of how the Reformasky method occurs, right? The first one is that you take your alpha halo ester, right? Now, and then react it with the zinc, right? So the zinc insertion is the first thing that will happen. The zinc will insert itself between the bromine and the carbon that was initially directly attached to the bromine. Now, this particular step is a very serious step. Very serious step. Very serious step. Now, the insertion of the zinc between the bromine and then the CH2 here will make the electrons on the carbon more available. Now, at this point, the electrons are not available at all. When the zinc is inserted, what we call this enolate intermediate, the zinc enolate intermediate here. Now, the insertion of the zinc will make the electrons on the carbon more available for donation, more available for donation. And so in essence, what we are saying is that the insertion will change this compound into a good nucleophile. Now, why a good nucleophile? Because as I said already, I mean, the insertion will make the electrons on the carbon available so that it can attack this carbonyl carbon. Now, let me give you a property about this carbonyl carbon. The electronegativity difference between the carbon here and the oxygen here is wide. And so the oxygen here is partially negative, the carbon here is partially positive, right? Good. And so this carbonyl carbon is an electrophile. It's an electrophile, right? So after the insertion, the electrons are available and then they can attack the carbonyl carbon. They can act, and then the reaction mechanism has been shown here. So first of all, we have the insertion of the zinc, and then it will make these electrons more available. Once the electrons are more available, they can attack the carbonyl carbon, right, to form this zinc alkoxide intermediate. The zinc alkoxide intermediate. Now, after getting your zinc alkoxide intermediate, what we have to do is just to hydrolyze the zinc Br, the ZnBr, and then we'll come and get what? We'll get our beta hydroxy ester. And this is Reformasky. This is the schematic representation of Reformasky. The first method, the insertion of your zinc to get your nucleophile. The next one is when the nucleophile attacks the acetone, right? Attacks the acetone to form your alkoxide intermediate. And then the last one is when you hydrolyze your alkoxide to form your acid. Now, what is down here reads, the Reformasky reaction takes place only with esters containing bromine in the alpha position and hence necessarily will yield a beta hydroxy ester. Always the Reformasky will yield a beta hydroxy ester. Now, this is an example for us to look at. What we'll pay attention to at this point is how to convert the reactant to products, just how to convert the reactant to products. Now, once we are able to do that, we have to also be able to convert the product to reactant. Now, chemistry is a science and chemistry is an art. When I am converting reactant to products, I am not doing any science, I'm doing art. So you pay attention to the art, right? Now, first of all, we have to look at where the reaction occurs. The reaction will occur between this carbonyl carbon and then the carbon that bears the bromine. What you do is that, let me bring this, okay. So what you will do is that first of all, you remove this bromine, right? Remove the bromine. That's if you are predicting. This is no mechanism, this is art, right? And then this carbon will directly bond to this carbon. So directly bond to this carbon, right? And then reduce the double bond. So remove it to a single bond and then add hydrogen here, and then you are done with your product. That is the product you get from Reformasky. That is the product you get from Reformasky. Very simple. if I'm looking at the example, and that is this product here, right? So this is the carbon that used to have the carbonyl, the double bond O. This is the carbon that bore the Br. And what has happened? They are put together directly. What has gone away? The Br has gone away, and then the double bond has reduced to an OH. Now, if I want to convert the same product to the reactant, this is what I do. I have to cleave between the carbonyl carbon, right? The carbon that used to bear the carbonyl. Cleave here, cleave between these. Let me change the ink. Cleave between these two. Now to the one, the ester part, I will add my Br, and then to the carbon here, I'll add my double bond. Remove the hydrogen and then reintroduce the double bond, and I'll have these two back. Now the examples will change, right? We'll get more complicated examples. So let's just hold on. Now the next one, same thing. I would remove this Br, reduce the double bond here to an OH, right? And then connect this carbon directly to this carbon. If I'm writing this product, I'll first of all write this carbon C. Around the C, I'll have an OH. I will have a CH3. Now I can bring this H here down. Then the next bond directly bonded to this carbon. Right, the Br is no more there. I'll have CH3, CO2 ET, and then I'll have CH3. That is it. That is that for that. Good. Now, the notes that has come down here is after your reformaski, you can further process your product. And so this is what we get from reformaski. Now, what we have here is a dehydration product. So we have removed water. When you remove water, you form an alpha beta unsaturation. An alpha beta unsaturation. Now, this typically will tell us the effect of heat. The effect of heat on a beta hydroxy ester, which we can extrapolate to be the effect of heat on a beta hydroxy acid. It forms an alpha beta unsaturation, as we can see here, right? And then we can hydrogenate this to get a normal alkyl group here, a normal alkane group here, a normal alkane group here. Now, what we can do again is to hydrolyze this ester group. Hydrolyze this ester group. We hydrolyze with acid to get a normal carboxylic acid functional group there. Very simple. Now, a question. The question has asked us to write the structure for compound A through to D. So A. Now, A, what has happened? We have a halo, an alpha halo ester, and then zinc. What the zinc will do? The zinc will just insert itself between the two. We just insert itself between the two. That will be the products. Just an insertion of the zinc between the carbon and then the bromine, right? Now, the next one, we are adding acetone. This is acetone. So if I'm adding acetone, now the insertion here will make these electrons more available, these two electrons more available. So they can attack this carbonyl. When they attack this carbonyl, the double bond here will break. So that I'll have an OH. So double bond here will break and I'll have an OH here, right? And I'll have an OH here. So if I'm writing this product here, I'll first of all, of course, and then there's water. So water, what we will form as an intermediate. Now, we wouldn't have had the OH, we would have OZNBr. And then when we add the water, it will change to OH, right? So I've done the two together. If I'm writing the product, I'll bring the C from this one. So C here. Now around the C, I'll also bring the C. So these two are the ones that are really bonded. So this is this one, right? Now around this, I have CH3, I have CH3, and I have an OH from this side, right? Now around this one, I have two H groups, so H2, and I have COO, C2H5, and that will be my product. Right now, this is not science, this is art. So you follow the art, very simple, very simple. So this is the answer. This is the answer. Now, the next one, we have gotten this product. We are being asked to convert it to product C. Now, what is happening? First of all, they are adding an acid. Now, what the acid will do is to first of all hydrolyze this. Hydrolyze this. So the acid can hydrolyze this, and then we'll have an H there. So it will become COOH. Now, the acid and the heat, the second round is the heat. The heat can also dehydrate. So the dehydration, remove water here. Now, the removal here is following ZTF. I want to explain that we have an alpha beta unsaturation not out of tradition, but because of ZTF. ZTF is that when in simple terms, the poor gets poorer. So when we are doing the elimination reaction, as we have here, and we have to remove hydrogen from the species around here, we have to remove the hydrogen from the one that already has fewer hydrogens. The poor gets poorer. Right? So this one has 2 hydrogens. We remove the hydrogen from here, 1 hydrogen from here to leave only one, leaving only one. Remove the OH from here, and then the double bond will be formed between this one and this. And that's what we'll get to. 2 changes will occur in the compound. First one is that we will hydrolyze the ester functional group here. Right? The ester group will hydrolyze to a normal carboxylic acid. The next one is that we will dehydrate to get an alpha beta unsaturation, and that is what we have here. Now, the last one is when we are adding hydrogen, excess hydrogen in the presence of platinum catalyst. Now, this is an addition reaction. The alkene functional group will break. The alkene functional group will break. That this one can form an extra bond, this one can form an extra bond. There will be hydrogen here and hydrogen here. And that's that for that. That will give us this product. This is a normal carboxylic acid. Now, we are saying we have to use reformers key to prepare the following. And so the following are products, right? Now we have to use reformers key. That means you have to predict the reactant. We have to predict the reactant. So let's work on that. Now, very easy anyways, very easy. What I have to do, I have to redraw this whole compound to make it look simpler. Now, when you see any of these in brackets or parentheses, it means they are substituents. So what I have is, first of all, I'll draw this C. Now, this C is here. Around it, I have CH3, and then I have another CH3 here, right? Now, the OH here will be on this carbon. So, OH. And then I'll have come here. Now this is the C I'm writing CH2 COO C2H5. Now what I have to do to get my reactants is first of all identify the alpha carbon. This is the most important group. This is the alpha carbon. Now this, of course, there's O here, so it's even simple. Now this is the carbon that bears the O. The carbon that bears the O. So this will be my next carbon of priority, the beta carbon, right? Now I have to separate the alpha from the beta, divide the alpha and beta. So to the alpha, I'll add bromine. When I add bromine, I am done. I have to make sure this is an ester, and it's an ester, so I'm done. Now to the beta side, I'll remove this hydrogen and bring a double bond here. And this will give me the aldehyde or the ketone that I have to use. In this particular case, it's a ketone. Then I'll add my zinc metal. Very simple. And these are the reagents I need to form my product. The answer will be given shortly. Now, that's what the same thing. So I'll have pH. I'm rewriting the structure. CH3. There's an OH here. Right. CH3, COO, C2H5. Right. Now, I always said that, I've said already that whenever you see the OH in parentheses, it means it's a substituent. So that's what we have done. Now, let me identify the alpha carbon. This will be the alpha. This is the most important group. This is the alpha carbon. Now, this could be beta. This could be beta. So we have to identify which one is beta. This is easy because, there's oxygen here. So you know that this is the beta of importance to us, right? This is the beta of importance. Even this is still beta anyways, but that's not what we are looking at. Now we cleave between the two, cleave between this and this, right? Cleave between them. Now to this side, we add bromine. So bromine should be attached to the side. To this side, we remove the hydrogen and then introduce a double bond. This is pure arts, no science. And you have your reactants. You make sure this is an ester and it's an ester, so we don't have a problem. This is a ketone. Then we add our zinc metal. We add that. Now the last one, it has no parentheses, so I can maintain this and divide. I have to find my alpha carbon. This is the most important carbon. This is my alpha carbon. Now this could be beta. This could be beta, right? But this is the beta we are looking at. How would you know? Usually the reaction occurs between, the unsaturation occurs between the alpha and beta carbon. That's what we call it, an alpha beta unsaturation, right? That can give it away. The unsaturation occurs between the alpha and then the beta. So we have an alpha beta unsaturation. Very simple. So we'll divide between this side and this and this. Now, sometimes the identification gets more difficult, so you have to use a lot of methods to know which one is the beta. The alpha is always easy because the CO group would always be there, but the beta is the issue, right? So this is the beta. Now divide between these two. When I divide, right, to this side, I'll add bromine. Now when I add bromine, because it was a double bond, this will not form a complete one, right? There's still something I have to do about it. See, it's a double bond, right? So when I break the two bonds, the carbon here has an opportunity of forming two bonds, not one bond. All the others I have been doing, the carbon would have had an opportunity to form only one bond because I break a single bond. Now I am breaking two bonds. So of course, I'll have to add bromine, right? But in order for the carbon to form four bonds, I'll have to add a hydrogen, and I am done. Now, in the next one on the beta carbon, is double bond, and I'm doing double bond O, so that is fine. I have no problem because I broke a double bond and I'm coming to introduce another double bond, right? I have no problem. So this will be one of my reactants. Now the bromine one, you have to always make sure it's an ester because what we use in reformaski is not the acid. We use an ester, an alpha halo ester. And so this is not an ester. This is a carboxylic acid functional group. So we have to remove this hydrogen and put either ET, right? We can put ET there, which is C2H5, ethyl group. And now we have our ester, and this is correct. Or we can put C2H5 there, and that is fine. We are now correct. That is how we tackle this particular question. The answers are in the slide. Right, the same thing we discussed. Now, the next question, we are asked, what starting material would you need for the synthesis of the following carboxylic acid using reformaski reaction? So this is the most difficult you can find. Now, first of all, this is the most important group, the alpha. There's no argument on the alpha. Now, this is the beta because this is the only one attached to the alpha, only carbon attached to the alpha. So what we do is that we would break this bond. When we break this bond, we'll add a Br to the side. When we add the Br to the side, so this side will now be coordinated to a Br. We have to make sure this is an ester. This is not an ester. So remove the hydrogen, put C2H5. Never forget to make sure it's an ester. It's an ester. So this will be one of the starting material. When you come to this side, right, now we have to put double bond O. Double bond O. We have broken one bond, so we cannot put double bond O. And there's no O there already. So what we can do is that we have to also break this bond. Remove this hydrogen. This hydrogen possibly came from the hydrogenation step. It wasn't part of the original compound, so we can break it. And now once we have broken this bond and this bond, we'll put double bond O there. Now remember, don't go and bring the ethyl groups because when we are doing the schematic pathway, we didn't introduce any carbon or any ethyl group, but we introduced a hydrogen, right? So we can remove the hydrogen confidently. That is that for that. Now, if you come to this side, same thing, this is the most important group. This is the alpha. Now, this can be beta, this can be beta, right? But then if you look at it very well, this is beta, this is beta. So this is just a rule of thumb, or maybe from experience, when you have done it for a long time, you'll be able to identify, right? And then these two hydrogens would possibly come out of a hydrogenation reaction, which came out of an alpha beta unsaturation. Right, so we just use some of these rule of thumb to determine. Once you're able to determine your beta, you can just divide between the two. Now I'll put Br to this one. This I'll change it to C2H5. Now when I come to this, I'll remove this hydrogen. I'll remove this hydrogen and put double bond O. Right, so that will be what I would get. Very simple. Now that's always remember to also add your zinc. Add your zinc. The next set of questions. Now, I'm supposed to describe how the following will be prepared. Now, this is art. This is not science. This is art. Chemistry is a science and it's an art. And what we are doing here is an art. the first thing you do is that you have to locate your carbonyl carbon. This is my carbonyl carbon. You don't have to think carbonyl. This is my carbonyl carbon, right? Now I have to then identify my alpha carbon. This is my alpha carbon. When you identify your alpha carbon, you don't have to worry yourself about the carbonyl carbon again. Then after identify your beta carbon, this is my beta carbon. Then I'll cleave between the alpha and the beta carbon. To the alpha part, I'll add a Br. Make sure it's an ester, it's already an ester. I am done. Now to the beta side, yes, remove this hydrogen and then bring a double bond here. Now I am also done. Then add zinc. You are done. No science, just add. If you come here, now this is your alpha carbon. This could be beta and this could be beta. But then this one is easy because you can see the O somewhere. Around the O is there. I mean, that is the beta. So quickly, what do? You cleave between the alpha and beta. When you cleave between the alpha and beta, to this, you add your bromine. You make sure it's an ester. This is not an ester, so you remove this. You can put CH3 or C2H5, and you are done. You have gotten the side. To this side, what do? You move the hydrogen and introduce a double bond, right? And then you are also done with the side. Then you add zinc. No signs, just add. Now, when you come here, the same thing. This is the alpha, and this is the beta. Always you have an alpha beta on saturation. Divide between the alpha and beta, right? Now, this is double bond. So this carbon has an opportunity to form two bonds. So 1, 2. Now to one, you can add bromine. To the other one, you have to add a hydrogen so that carbon can form 4 bonds. You have to also make sure it's an ester. So remove the hydrogen from here, C2H5. I'm done. Now, if you come to this side, you've broken a double bond. You have to introduce the double bond O, so you don't have any issue. Just take this double bond, bring it here, and then double bond O. We are done with this side. You add zinc. When you come here, the last one, the same thing. You don't even have to think about it. It's an art, not a science. Now, this is alpha, this is beta. Cleave between alpha and beta. Add bromine to the carbon here, the alpha carbon. Now remove the hydrogen from here and then bring a double bond and you are done. You add zinc. This is already an ester, so we don't have a problem. That is how we do it. Very simple, easy peasy, lemon squeezy. Now let's talk about reactions of hydroxy acid. Now the reactions come in two folds. The first one is that we have two functional groups. We have a hydroxyl group and we have a carboxylic acid functional group. There are reactions that only the hydroxyl group will undergo. We have reactions that only the carboxyl groups will undergo. So we'll talk about the two of them, and later we'll talk about the effect of heating on the hydroxy acids. So the first one, we are looking at reactions of the carboxyl functional group, the COOH group. Right now, without thinking, because an acid group, the first reaction is a salt formation. That's a neutralization reaction in essence. So we have this acid part plus the base, and then we form the salt, right? We form a salt and water, this acid-base reaction. Now we have the same acid plus a bicarbonate, right? Still will form salt and then water. Because it's a bicarbonate, we have to form carbon dioxide. So the reaction proceeded for us to form carbonic acid. The carbonic acid will further disintegrate to give us water and carbon dioxide. Very simple. Remove the hydrogen, add Na, right? And then this hydrogen will come and then attach to this to form the water. Very simple. There's no mechanism. All right. Now we can also form amide. So for you to form amide, you add ammonia and then you heat it, right? Add ammonia and then heat, and then you form your amide. How do we form our amide? This whole group goes away. Then we have NH2, right? One of the hydrogen here goes away. Add to the OH to get you the water, right? Very simple. This is not the mechanism once again. This is the art, how to find your product, how to get your product. Now, ester formation, right? So when you have the acid plus alcohol, you can form an ester, a sweet-scented product, right? So that is what we have here. Now, what will happen? The OH here will go away. The OH here will go away. The H will go away. And so the oxygen here will directly bonded to this carbon. And that is what we have here, right? That is what we have here. Very simple. Very simple. Now, reactions that the OH side will undergo. The OH side, the first of all, undergo halogenation reaction. It's just a reverse of how we're forming the alpha hydroxy acids by adding 2 moles of sodium hydroxide and then acidifying it. Now we are coming to reverse it. If we have a hydroxy acid, you can also add chlorine, right? You can also add chlorine or any other halogen at where the OH group is. So this is what we have. Now we have the OH group, we add HCl, and then the chlorine will be substituted at this on the beta carbon where the OH was initially. Very simple. Now we can also undergo oxidation reaction, right? Now this oxidation reaction will further oxidize the OH group to a carbonyl, right? Oxidize the OH group to a carbonyl. Now this can be strong oxidation. Actually, this should be strong oxidation, right? Strong oxidation. Now what we have formed here is what we call a keto acid. We will talk about it in the next video, not this one, right? So that will be everything for the hydroxy acids, right? The hydroxy acid when it comes to the reaction of the OH path. Right. Now, the next step of reactions that we are talking about, the next set, we'll talk about the effect of heat, on hydroxy acid. Now, the behavior of alpha hydroxy acid under heat is different from that of beta and that of gamma and delta. So we'll talk about each of them, right? Each of them. Now, the first one is alpha hydroxy acid. When you heat alpha hydroxy acid, 2 moles of the alpha hydroxy acid will condense. Now they will condense to give you a cyclic compound that we call a lactide. Right? A lactide. Now that lactide is formed from as a result of intermolecular dehydration, right? So this is the illustration, very simple. Now what we have here, we have an alpha hydroxy acid. So this is the carboxylic acid functional group. COOH is a COOH. So we have COOH here, right? Now this is the alpha carbon directly bonded to this one. This is the alpha carbon, right? The OH is on the alpha carbon. If you come here, think the same alpha, right? So COOH here. Now we have turned it upside down, so they are facing themselves like this, right? COOH group here. This is the alpha carbon bearing the OH. Now what will happen here is that at this side, the OH group here will go away, and then the H will go away. This would directly be bonded to this one. The O here will be directly bonded to this carbon. Now on this side, the same thing. The OH will go away. The H here will go away, right? And then this one will be directly bonded to this oxygen. And that will form what we call the lactide. This cyclic compound called the lactide. Very simple. Don't have to even think about it. Now, the behavior of gamma and delta are the same, right? So in acidic solution, gamma and delta hydroxy acid form cyclic esters, and the cyclic esters are called lactones. Right? Now, these two will easily form cyclic esters because when they cyclize, they form a 5-membered and a 6-membered ring. And from our normal chemistry, we understand that these are the two most stable forms of the ring, the 5 and the 6-membered form, with the 6 being more stable than the 5, right? Good. And so that is what we have here. Very simple, very simple. If we have gamma hydroxybutyric acid, now it will undergo what we call intramolecular dehydration. That means within the same molecule, the molecule will bend and react with itself. Within the same molecule, we will lose water for the cyclic form to form. And so that is what we have here. This is the carboxyl functional group. This whole thing, this is the OH functional group. In the same compound, it will bend such that the OH group here is lost, the H is lost, and there's a direct bond between the centers, right? And that's what will give us the 5-membered ring, the 4-butanolide. Now, when it comes to the delta, the same thing, the OH will go away, the HA will go away, will form a direct link between this, and that will give us the 6-membered ring, right? The 6-membered ring. The pentanolide is 5-pentanolide. Very simple. Now we are saying cyclic esters are called lactones. We've mentioned that already. A lactone is formed from an open chain of hydroxy acid in which the hydroxyl group has reacted with the acid to form an ester. Now we are talking about lactones. We are saying that lactones are cyclic esters derived from intramolecular esterification, esterification or dehydration. Dehydration because there's loss of water. Esterification because you see the reaction here is a reaction between a carboxylic acid and alcohol, a hydroxyl group, right? And that's the esterification reaction. That's a esterification reaction. Now, we are saying lactones are known with rings of all sizes from 3 to 20 or more. Although 3 and 4 membered rings are extremely unstable. The easiest to synthesize are 5 and 6 membered lactones because they are more stable, right? But there are many larger ones found in nature. Lactones, like other esters, are hydrolyzed in aqueous acid and base. Now, this statement is very important. I will use it to explain something. If we have the lactones as we have here, now the question is for us to identify the lactones. So let's quickly identify them. Now, the lactone would have a carbonyl directly bonded to each. So this ester group here. So this is a lactone. Now, this one, the same group is here. This is a lactone. Now, this side is a lactone, this side is a lactone, but the two are there. When the two are there, it's not a lactone again. So this particular one is a cyclic anhydride. So this is not a lactone. This is a cyclic anhydride, but this is a lactone and this is a lactone. Right. Now, what I wanted to talk about, if you have a lactone like this, now in solution, in aqueous and acidic or basic solution, what will happen is that this chain, this can break again. This whole thing can break. It can break so that you can have your open chain. You can have your open chain with the normal carboxyl group and the normal hydroxyl group. So there are compounds in which when you look at the structure, you might not see a hydroxyl group there, right? You might not see a carboxyl group, there, but they are still called acid because when they open up in solution, they expose a carboxyl group. They expose a carboxyl group. I'll explain further when I go on, but just take note of this statement for me. Take note of this statement for me. All right, so B and C. Now, we talked about alpha. We said when alpha molecule is heated, right? When the alpha hydroxy acid is heated, 2 moles would form a lactide, or condense to form a lactide. Then we jump over the beta and then went to the gamma and delta, say that a single molecule will undergo intramolecular esterification or dehydration to form a lactone. Now let's look at what happens to beta. We've already talked about this, but not explicitly like this one, right? So we are saying that beta lactones have been detected as intermediate in some reaction, but are unstable. Because they are unstable, they will not form largely, right? Now, they are highly reactive. However, in an attempt to prepare a beta lactone from a beta hydroxy acid, elimination usually occurs instead. And when you heat the beta, this is the alpha carbon, this is the beta carbon, right? When you heat this, it undergoes a dehydration step, right? A dehydration to form an alkene. So what will happen is that this OH will go away, this H will go away, and there will be a double bond formed between the alpha and beta. Now, the reason why this H is the one that goes away is because of the ZTEF, right? ZTEF, which says that the pore gets poorer. So between this, which has 3 hydrogens, and then this that has 2 hydrogens, this is the one that will go away, right? So we'll form an alpha beta unsaturation. An alpha beta unsaturation when we heat a hydroxy acid. Now, this has been demonstrated here. If I have a beta hydroxy acid like this and I heat it, I have an alpha beta unsaturation. I will not form a lactone because that lactone is not stable. Now, these are examples of lactones in nature. You have to keep at least one example in your head, right? Simplest, the most common of them is erythromycin here. You don't have to know the structure. This is the example, it's fine. And then vitamin C2. Now, vitamin C is called ascorbic acid. Why is it called ascorbic acid? Clearly, there's no acid here. There's no acid in this structure. So why is it called ascorbic acid? Let's explain. The first one was what I was trying to explain formally. That this is a lactone. This is a lactone. This is a lactone. Right now, in solution, this lactone can open up again. Remember, the lactone is formed from an intramolecular condensation of a carboxyl functional group or carboxylic acid functional group and a hydroxyl group. So in solution, the compound can open up. Now, when it opens up, it would have a carboxyl functional group and a hydroxyl functional group. And that is the reason why we see, even though we don't see any acid functional group, we see it is what? It is ascorbic acid. But this is not the main reason. This is one of the reasons. The main reason is that now this compound would behave as an acid because of the enol functional group, the enediol functional group. Right? So this is an alkene, this is an alcohol. When you combine them, is enol. So enol, two enols actually. So we say it's an enediol. Right? These things are bonus points for anybody watching the video. Enediol. Right? So what we have here is that now this O each here, one of the H's can be donated, right? One of the H's polar, so it can be donated. Essentially, I'm looking at this one, right? Can be donated. So in solution, the compound will donate this hydrogen, can easily donate this hydrogen. It's a weak acid, but can donate the hydrogen, right? Once it's donating a hydrogen, it's acting as an acid, right? Now, because it can act as an acid because of the enediol group here, that is another reason, or actually the main reason why we call it ascorbic acid. So two reasons. The first one is that the lactone can open up, exposing the carboxyl functional group, right? The next thing, which is the most important one, is that the enediol, this is how we write enediol, E-N-E, sorry, E-N-E-D-I, enediol, right? So the enediol functional group, one of the hydroxyl groups there, can donate the hydrogen in solution. So this whole compound behaves as an acid in solution, right? So we call it an acid not because we can see a carboxyl group, but because of the behavior of the compound in solution. That is that for that. Now we have a question to try. We are seeing, right, the structure for the lactone formed, right, in the presence of. So they have given us a gamma hydroxybutyric acid. We've seen it already. It's not anything to write home about, right? Now this is butyric acid. 1, 2, 3, 4. 4 carbon COOH. Right. Now we are looking at gamma. This is alpha. This is beta. This is gamma. Right. So gamma hydroxy. That means the OH is here. Now if I'm filling it, this is CH2, CH2, CH2. Right. Now what will happen is that the OH here will go away. The H here will go away. This would directly be bonded to this one. If I'm drawing it now, I would have to have a 5-membered ring. So let me draw the 5-membered ring. Well, I would have 1, 2, 3, 4, 5. The oxygen will be part of the ring, right? The oxygen will be part of the ring. And so now this one will be my carbon 1, my carbonyl carbon, directly bonded to the oxygen here, right? Now there are bonds here all over. This will be CH2, CH2, CH2. Now this is my compound. This is my very simple. Now the next one, we have will form is the same thing in the slide. Will form a 5-pentanolide. If I'm drawing my 5-pentanolide, now this is the actual compound. Let me draw the actual compound. 1, 2, 3, 4, 5. OOH. Right now the hydroxyl is delta, so it's here. Right, this is CH2, 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 CH2. Now, essentially, what will happen? This OH will go away, this H will go away, the oxygen will be directly bonded to the carbonyl carbon. Now, we are getting a 6-membered ring. If I'm drawing my 6-membered ring, 1, 2, 3, 4, 5, 6. The oxygen will be part. This will be my carbon 1, directly bonded here. There are bonds all over. Right. Now, this is H2, 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 H2. Right. So this is my 5-pentanolide. Now, if Yes. Now, if let's say we had a substitution there, something like this, instead of maybe we having CH, instead of we having CH2, we had CH and then CH3 here. I would have to find this carbon. So this is carbon 1, and it's carbon 1 here. This is carbon 2, 3, 4. So on carbon 4, there's substitution, right? Now this carbon 1, carbon 2, carbon 3. On this carbon 4, I wouldn't have written CH2. I would have written CH, and then there will be a substitution here, CH3 here, right? So we just pay attention, look at the changes. The only place where there will be a change will be between the OH and then the CH3. Make sure you represent the other species well. They will not be affected by the heating process, but represent them well when you come to the ring structure. Very important. Now, the next thing we are supposed to look at is we are supposed to form lactic acid from this. We've seen this before. Lactic acid, you have to know the structure of lactic acid before you can solve this question, of course. And the structure of lactic acid, we have CH3, C, COOH. There's an OH group here, and there's a hydrogen here, right? There's a lactic acid. Now, if you look at this and compare to this, you realize that the lactic acid is 1 carbon length longer than this one. That will indicate that we have to use the hydrolysis of hydroxynitrile. So we'll take this compound, right? CH3, C double bond OH. Now this is the compound. We add HCl. We add HCl. When you add HCl, what will happen is that this double bond will break. The H will be here. The Cn will be substituted here, right? Now when you get this, the next thing that you have to do is you have to hydrolyze, right? Hydrolyze this using the acid. When you hydrolyze this, you come and get COOH, and this is lactic acid. This is lactic acid. This is lactic acid for you. So that's for that. It doesn't get any difficult. It doesn't get any difficult. Now, the question is asking us to give examples of what will happen when we heat the following. Now, when you heat an alpha hydroxy acid, you get 2 molecules of the alpha hydroxy acid condensing to give you a lactide. We've talked about it. Now, when you heat a beta, would have dehydration, right, to form an alpha beta unsaturation. Alpha beta unsaturation. If it's gamma or delta, the last two. Now, in the case of gamma, you have an intramolecular esterification or dehydration to form a butanolide, a 5-membered ring. Now, in case of the D, right, which is the delta, you'd have intramolecular esterification or dehydration to form a pentanolide, 5-pentanolide, which is a 6-membered ring. Very simple. Very simple. Now, the last question for hydroxy acids I have explained, right? When I got to the example, the natural example is vitamin C is ascorbic acid. If you examine the structure, there's no carboxylic acid. Why the name ascorbic acid? So first of all, I said the acid there is not because of the structural representation, but because of the behavior. The dienol part can donate a hydrogen. The hydroxyl group at the dienol part, one of them can donate a hydrogen, and in essence, making the compound act as an acid. The next one is that in solution, the lactone part will open up. When they open up, they will expose a carboxyl group. So even though carboxyl group is not apparent in the structure, in solution, right, the compound will have to act as an acid. So in solution, you will see a carboxyl part exposed because of the opening, right? Now in solution, there will be an equilibrium between the carboxyl part and then, yes, there will be an equilibrium between the open chain, right, and then the cyclic one. So there will be an equilibrium reaction between the lactone and then the open chain with the carboxylic acid and the hydroxyl group, right? And so in solution, you will actually see the carboxyl functional group. I don't know how you go and see it, but in solution, the carboxyl functional group is apparent, right? That's now. As always, the question is that this material is a supplementary material, not an alternate material to what you have in your class. And if you have any question, can either get to me or get to any member of the HESA academic board. Thank you very much, and have a nice day.